In this unit, we're going to be looking at how we can, quote unquote, count atoms and molecules, even though they are very, very small particles, and we usually deal with a whole lot of them all at one time. And all of these concepts from that we're going to talk about in this unit all are derived from this concept of the mole. And I'm not talking about a growth on the skin or, a little burrowing animal. The mole is something that we use to help us quantify and organize a large number of things like looking at atoms or molecules. So I want you to imagine a drop of water. Imagine how small that is. A drop of water contains about 1.5 to about 1.7 sextillion water molecules. Okay, well, what is that? I'm going to put it in scientific notation. That's 1.5 times 10 to the 21st to about 1.7 times 10 to the 21st. If I'm going to write that out, let's see if I can get the right number of zeros here. 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go. So that's 1.5 sextillion written out completely. Um, and how do we manage counting all of these atoms and molecules? So to deal with a large number of very, very small objects, we use something called the mole. I want you to think of the mole as a chemist's dozen. Just like a dozen of something, like a dozen atoms, means there are 12 atoms. A mole is kind of a way to group up a large number of atoms. 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. Now, just to kind of take a little side trail here, this number right here is known as Avogadro's number. And you do need to memorize this. Okay, you should know what a mole of something is, 6.022 times 10 to the 23rd. Now, one thing I do want to highlight it is that there is more decimal places. So this is a rounded off number. So remember that for your sig figs, this version of the number only has 4 sig figs. Okay, so how does that help us group a large number of things? Well, let's go back to our example of a drop of water. I can figure out how many moles of water I have in that drop by doing some conversion factors. So there's 1.5 times 10 to the 21st molecules of water. I'm just going to abbreviate molecules in 1 drop of water. So how many moles is that? Well, if I want to uh, cancel molecules out, I'm going to use Avogadro's number, 6.022 times 10 to the 23rd molecules of water in 1 mole of water. So if you look at this, those units cancel out, and that comes out to about 0.0025 moles of water per drop, or in 1 drop of water. And that's a much easier number to deal with than, um, you know, 1.5 with a bunch of zeros after it. And so this allows us to quantify a large number of atoms. So let's do an example. How many atoms of carbon are in 2.5 moles of carbon? Now this can be set up by, or this can be answered by setting up a unit conversion. We're given 2.5 moles of carbon, and we know, or hopefully you memorize fairly quickly, a conversion factor that will get us from moles to number of things, in this case, atoms. So we want moles of carbon to cancel out, and we know that by using Avogadro's number, there's 6.022 times 10 to the 23rd atoms of carbon in 1 mole of carbon. So the moles cancel out, and that comes out to 1.5 times 10 to the 24th atoms of carbon. Using the mole terminology makes life simpler for us versus having to look at these very large complex numbers. And in fact, they represent the exact same thing. Just like 1 dozen donuts is 12 donuts, 2.5 moles of carbon is the same thing as saying 1.5 times 10 to the 24th atoms of carbon. It's just much easier to say this than it is to deal with like very, very large numbers. So with that in mind, let's talk about how we weigh out moles. Okay, let me kind of put this into context here. How can I weigh out 1.85 times 10 to the 24th atoms of copper? I mean, that's virtually impossible if I try to do that individually. Like I can't, pick an atom of copper up, and put it on the balance. Like that's impossible to do individually. But if I were to convert that into moles, that's a much more manageable number. So I'm going to take the 1.85 times 10 to the 24th atoms of copper, and I'm going to use Avogadro's number. I want atoms to cancel out, so I put that on the bottom, and I'm going to put moles on the top. There's my conversion factor. So those cancel out, and that comes out to 3.07 moles of copper. Now, this is a much more manageable number. But I can't weigh moles on a balance. Like our balances don't read moles. Our balances read some unit of mass, like grams. So we need a relationship or a conversion or something to go from moles to grams. And this is where the periodic table is going to help us out here. So if we were to look at the periodic table and kind of zoom in on carbon here, usually at the bottom, underneath the element, is listed the atomic mass. So we learned earlier that this number represents that one atom of carbon weighs 12.011 AMU, atomic mass units. Okay, that's great, but that doesn't help us like comparing moles to an actual unit of mass, like grams. Well, what we can do is now use that same number and the terminology of using a mole to relate it to mass. 1 mole of carbon atoms weighs the same number, 12.00011 grams per mole. And we call this molar mass. or I might use the abbreviation MM. So when you look at the periodic table, not only does it tell you how much that atom weighs individually in units of atomic mass units, but this now tells you that 1 mole will weigh 12.011 grams, and that's the molar mass. So on this little side picture here, this kind of just shows you what 1 mole of each of these elements looks like. It's not something I want you to memorize or have to, account for or anything like that. But just kind of giving an example of, these are 1 mole of each material. Notice something important here. Does 1 mole of a substance equal the same mass of other substances? No, because if we look at zinc, 1 mole of zinc is 65.4 grams, but 1 mole of um, copper, I'm sorry, carbon weighs only 12 grams. So equal number of moles does not necessarily mean equal mass. It depends on the molar mass of the element or the molar mass of the compound. We'll get into that in a little bit. Notice if I look at an atom like lead, lead's molar mass is much higher than um, than carbon's. And the units again that we use for molar mass is grams per mole. So for every mole of lead that you have, it weighs 207.2 grams. So if you had 2 moles, it would weigh double that. If you had half of a mole of lead, you would divide that number by two, and that would um, get you to the how many the grams. So now let's go back to the original question on this slide. How do I weigh 1.85 times 10 to the 24th copper atoms? Okay, well, up above, we just said that 1.85 times 10 to the 24th copper atoms was 3.07 moles of copper. So let's start there. 3.07 moles of copper. So we did this conversion above. Now let's continue on. If I want to get to grams, I need to use a conversion factor that has grams in it. Well, my conversion factor is going to be the molar mass. I want moles to cancel out, so moles will be on the bottom. I'm going to look at the periodic table, and the periodic table tells me that 1 mole of copper weighs 63.546 grams of copper. So moles cancel out. I plug that into my calculator. And after rounding to the correct number of significant figures, I get 109, I'm sorry, 195 grams of copper. Now let's do another example. How many moles is 0.72 kilograms of copper? Okay. So when approaching a problem like this, it's easy to get lost and be like, I don't even know where to start. Start by doing conversions. We're given 0.72 kilograms. Now I know that in order to use molar mass, this has to be in grams. So the first thing I'm going to do is set up a conversion to convert kilograms into grams. Hopefully you've memorized your conversions for the metric system. 1 kilogram is 1,000 grams. Now that I have grams, I can once again use the molar mass. So I look at the periodic table. I want grams to cancel out. Moles will be on top. The periodic table says that 1 mole of copper weighs 63.546 grams. So now grams cancel out. Notice the last unit I'm left with is moles. Using the right significant figures, that is 11 moles of copper. Now I'm going to take this problem one step further. What if this problem said how many atoms are in 0.72 kilograms of copper? Okay, well, I'm going to start at the same exact spot. But first, let me just highlight, I'm dealing with atoms. So it's probably a good bet that I want to get to moles as my first stop, or a stop along the way. So setting this up looks exactly like the problem I just did. So I'm just going to copy all this down. Okay, so now I'm at moles. Do I have any relationship? Do I know any conversion factor that relates moles to the number of atoms in a substance? Yeah, I use Avogadro's number. I know that 1 mole of copper atoms is 6.022 times 10 to the 23rd copper atoms. So moles cancel out. I'm left with the units of copper atoms, and that comes out to 6.8 times 10 to the 24th copper atoms, or atoms of copper, however you want to put that unit. And I want to highlight something important here. All three of these measurements represent the same exact amount of material. 195 grams of copper is 11 moles of copper, and 11 moles of copper is 6.8 times 10 to the 24th copper atoms. If I were to put 6.8 times 10 to the 24th copper atoms on a balance, it would weigh 195 grams. It's just a matter of, well, how do we want to represent that number of atoms? Okay, so with this in mind, let's talk about how we can do the same exact thing, but when we have multiple atoms bonded together to make molecules. How do we deal with this? Okay, so let's just jump right in with an example. How many moles is 14 grams of CH4? CH4, you don't have to know this, but that's methane. So I'm going to do the same thing. I'm going to start with what I'm given. I'm going to set up a conversion factor. So 14 grams of methane. And how do I go to moles? Well, I'm going to start, I want grams to cancel out. And if I knew the molar mass of methane, I could plug that into this conversion factor. Well, how do I find that? Get your periodic table and add up the mass of all of the atoms. So first step here is find the molar mass of methane. So I look up at the periodic table, one carbon atom, or if I'm going to use molar mass, 1 mole of carbon is 12.011 grams per mole. I get that right from the periodic table. I have 4 hydrogens in the formula, so I'm going to do 4 times 1.008 grams per mole. And so the total amount of hydrogen, or mass of hydrogen, is 4.032 grams per mole. So I add all that up. The molar mass of CH4 is 16.043 grams per mole. Now I got something to plug into um, my conversion factor. 1 mole weighs 16.043 grams. So grams of methane cancel out. I'm left with 0.873 moles of CH4. Okay, let's do another example. How much water should I weigh out to get 2.20 moles of water? Okay, so I'm going to start by setting up a conversion factor. I'm given 2.20 moles of water. And I know I can go from moles to grams if I knew the molar mass. So I'm going to take a little side trail, find the molar mass of water. Well, in water, water's H2O. I have two hydrogens. So that's 2 times 1.008. Too many zeros there. Grams per mole. So multiply that together. I have one oxygen. So that's 15.99 999 grams per mole. And I add all that up. So the molar mass of water is 18.015 grams per mole. So I'm just going to toss that into my conversion. 1 mole weighs 18.015. Cancel the moles out. All I'm left with is grams of water, which is what I wanted to get. And that comes out to 39.6 grams of water. Let's do one more. And this one's going to be a little bit, I don't want to say more difficult. There's going to be a little bit more to it because I'm going to rely, or I'm going to present a problem that requires you to go back and do some things that you did in previous units. How many moles are in 98.3 grams of aluminum hydroxide? Okay, well, let's start off by setting up a conversion, see if we're missing anything. 98.3 grams of aluminum hydroxide. And I know that I need the molar mass to go from grams to moles. All right, well, what's the molar mass of aluminum hydroxide? Well, I don't even have the formula of aluminum hydroxide. So how do I find the molar mass? Well, we did a little thing called nomenclature a little bit ago, where you needed to know, first of all, your polyatomic ions like hydroxide, and then be able to come up with the formula if you're given the name. So let's just kind of go from the basics. Aluminum, and it's an ionic compound, generally has a charge of +3. Hydroxide, hopefully you have that memorized, has a charge of -1. So the formula, I need 3 hydroxides in order to balance out the charge so that it is a charge of 0. Now you're gonna have to do that on an assessment? Probably. So you're not gonna be able to get away from knowing how to do, how to come up with the formula based off of the name of the compound. So now let's calculate the molar mass. One aluminum, I looked that up on the periodic table, weighs, so that's 26.982 grams per mole. I have 3 oxygens. and that's 47.997 grams per mole. And then I have three hydrogens. And I add all of that up and get a molar mass of 78.003 grams per mole. Just a little side note, kind of a rabbit trail here. One of the things that I noticed every now and then when grading the assessment, where you were finding the um, the mass in atomic mass units of like a compound, some of you weren't handling this parentheses the correct way. You were taking it as, well, I need to cube everything in there. So I'd take the mass of oxygen and take it to the third power. That's not what that three means. That three means is if I have an aluminum, that there are three hydroxides around it. And so that's a total of one, two, three oxygens, one, two, three hydrogens. So make sure that you are interpreting these formulas correctly. So now that I have my molar mass of aluminum hydroxide, let me kind of clean this up a little bit. So now I'm going to put grams of aluminum hydroxide, and I want grams to cancel out. So that'll be on the bottom. Moles will be on top. And 1 mole of aluminum hydroxide weighs 78.003 grams. Grams cancel out, and that comes out to 1.26 moles of aluminum hydroxide. Now, I highly recommend that you practice over and over. Practice this, look up the problems in the textbook, go through the homework checks. Make sure that you know how to do this, because we're just going to keep on taking this one step further and using these conversion factors and these types of problems to go back and forth between all of these quantities.